Okay, so thank you everyone for joining, and we are going to start this week's content on flow through unsaturated soils. And this course is instructed by Professor TV Bharat and PMRF teaching support TA for this course. My name is Satyam Tiwari, and coming now to the content of this week that we have studied in theoretical class that when a steady state is there, how we can understand the concept of steady state flow in the metallic rod. That if we maintain a particular temperature at both ends of the metallic rod, then in that case the temperature variation is like from the higher temperature to the lower temperature, and it will be something like this. Okay, so based on this, we can determine the temperature at different points. Okay, so in this case, temperature is varying linearly. Okay, so this is like the steady state flow of heat. Okay, similar concept is applicable in case of soil when high air entry discs are provided at both ends of this imaginary soil sample, and a particular head is maintained at end A as well as B. In that case, let's say head at B is lesser than head at A, then the flow will take place from A to B, okay, from higher head to the lower head. In that case, we can say that if these two heads are constant, this flux, which is going from this side to this side, is constant. Okay, so this is the steady state condition. Okay, the heads are constant at both ends, so the flux which is passing through the soil sample is going to be constant. Similar concept is applicable for infiltration as well as evaporation case in the soil. Uh, for like understanding this one, this is a cross section from a field, and we can see the water table is at this depth. And, that's going to be here. Let's say H naught, and we can say that the evaporation is taking place on the top surface, and this evaporation depends on the temperature also. And after a while, because they will be the when the water will be evaporated from this side, then this soil will be in the partially saturated zone or unsaturated zone. In that case, the capillary fringes will form and the water will rise up. After a while, a steady state condition will be established such that the flux which is going out will stabilize. In that case, the water which is getting evaporated will be the same as the water which is being drawn by the capillary fringes from the water table. Okay. So the height we are taking from here, the Z, okay, at Z is equal to Z1, the evaporation is taking place. Okay. So, so while we understand the concept of flow through soils, we also understand that it is not always like in the unsaturated soils, the Q is not constant. In some cases, like in the case of this vertical column, if a particular head is being maintained at the top, and the flow of water is taking place. So it can happen that the soil in this zone might not be saturated, but the soil in the middle zone is saturated due to the flow of the water, and these pores are filled with water, and therefore the water is flowing from here top to bottom, and a constant flow is observed. Okay, so this is not the case of saturated soil, but the unsaturated soil. Okay, but the flow is constant. So steady state flow can also take place in the unsaturated soils. This is one of the case. The steady state has been demonstrated, or the flow, the change in head is derived by the Richards in 1931. Then the Richard assumed that this hydraulic conductivity is a function of A plus BH, or a function of this head. So if we see in this particular soil mass, then we'll observe that if a head is maintained at this point, then K will be equal to A plus BH. Okay, A and B are the constants. And here for the horizontal flow, if we'll observe the head, then mostly head is what? Head is the elevation head. Okay, and we can say the osmotic pressure head, the metric head. Okay, and in the horizontal flow, because both the ends are at same elevation, so we can say the elevation head is zero. Okay, and the pressure head we usually do not consider in case of soil, and as if no salts are present, this osmotic pressure head will also be zero. So we will left out with the metric suction head. So this head which is here, that's mostly the metric suction head, until unless it's given that the osmotic pressure is present due to some salt. So if we'll derive it further, then we'll observe that the expression for K we have taken A plus BH, okay, which was linear. The uh, this hydraulic conductivity function was linear, linearly varying with H. But at the end, when we'll observe the function of the change in head, that will be equal to minus A plus under root of A square minus twice B Q into X upon B. So this function of H is not linear. Okay, it is varying non-linearly with X. So as the X is the distance from this end, X. So as the X is varying, this H will also vary, right? So in that case, we can say that the H is non-linearly varying with X, that is the distance. So the motto is to solve an example based on this formulation which we have observed from Richard 1931. Okay. So the example says, okay, so based on the formulation which we have observed, we'll be solving numerical here. And the numerical is that the steady state flow, let me take the pen. The steady state flow of water is taking place in a 100-meter long tube, and the length of the tube is 100 meter, and that is spaced horizontally. The head at one end is 0 meter, and at the other end is 360 meters. So we need to determine the flow rate and also calculate the variation of suction head over the length of the pipe. Okay, the values of A and B are provided here. So here a pipe is provided where steady state flow is taking place. The this side, let's say this side is A, this side is B. The X is considered as 0 meter. This side XB is equal to the length of the pipe is 100 centimeter. Okay, and then we have the head HA is equal to this is 360 meter. Head is higher at A, and HB is equal to 0 meter as its one end is at 360 meter head. Then we need to determine what will be the flow rate Q. Okay, the values of A is 8 centimeter per day and B is 0.02 centimeter per day. So we will make use of that formula which we saw. H is equal to minus A under root of A square minus twice BX twice QX into B upon B. So we'll write here H is equal to minus A plus under root of A square minus twice BQ into X divided by B. Okay. So here we'll write the value of H as, because this side is as 360 degrees, so that will be 0 minus 360 or 360 minus 368. And the value of A is going to be minus 8 plus the A square is 8 square minus twice into B 0.02. Okay. And multiply Q into X. The value of X is 100 divided by B, that's going to be 0.02. So if we solve it further, it will be minus 360 is equal to, in the numerator, minus 8 plus inside the square roots, that's going to be 64 minus 2 into 0.02 multiply 100 and 4Q divided by 0.02. Fine. If we solve it further, then we'll observe this becomes 360 into 0.02. That's going to be minus 7.2 is equal to minus 8 plus under root of 64 minus 4Q. After solving it further, we'll observe this will become minus 7.2 plus 8 is equal to under root of 64 minus 4Q. And further, if we process it, then that's going to be 8 minus 7.2, 0.8 square is equal to 64 minus 4Q. And the square of 0.8 is going to be 0.64 is equal to 64 minus 4Q. 4Q is equal to 64 minus 0.64. And then the value of Q is going to be 64 minus 0.64 divided by 4. Okay, so 64 minus 0.64, that's going to be divided by 4, it's going to be 15.84, right? So the value of Q is going to be 15.84. And the unit, how we'll determine? The unit of A was given as centimeter per day, and everything else was in centimeter excluding the head. Then it's going to be centimeter cube per day, right? So in that way, we have solved for Q, but also we need to calculate the variation of suction head over the length of the pipe. So how we can do that is that we can use the same expression again, okay? But this time we already know the value of Q. So we'll put the value of Q, but the unknowns will be X and H, okay? Then we will vary the value of X from 0 to 100, and we determine the value of head at each point, or the variation of suction head. Fine. So let's do that here only. So in this question only, if we'll do that, then H is going to be equal to minus A is minus 8 plus under root of A square is going to be 64 minus 2 into B is 0.02 multiply the Q value we have determined the flow at steady state, that's going to be 15.84 multiplied by X, that is unknown, divided by 0.02. Fine. So the variation of head, if we'll simplify, that will be equal to minus 8 plus inside the under root, it's going to be under root of 64 minus 2 into 0.02 into 15.84, 0.6336 x divided by 0.02. So now we know this formulation, and based on this formulation, we can say that the value of h will be varying based on the value of x depending on this expression. So we'll use this expression in our Excel sheet and we'll calculate the variation in the head values. Fine. So let me just take what are the values. Okay, so this is the formulation which we have observed, fine, and we'll determine the variation in head based on the values of x. Okay, so what we are going to do is first we are going to put the values of a and b. Okay, so the value of a is 8, value of b is given as 0.02, right? And the x we are going to vary from 0 to 100. So maybe we'll take interval of 5, 0, then we'll take 5, and similarly we will take on to 10, etc., etc., till 100. Okay, so 100. To determine the values of h, we'll use the formula which is provided here. So we'll type it in here that h is equal to, it's going to be minus the value of a, that is 8. Let's log this value. Okay, plus we put a bracket at the start, plus that's going to be square root sqrt, and inside the square root we'll have 64 minus 0.6336 times the value of x. X is nothing but a2, multiply a2. So this square root will close, and we'll close this bracket also, and whole will be divided by the value of b. Okay, let's log this one also. So we have written this formula, and if we will copy this whole formula for all the values, then we will observe the variation of head. And so the head at 100 centimeters provided at minus 360 degree, minus 360. Fine. So if we plot the variation of head against x, then we'll see that let's put the insert and the graph, and the variation is like this. Okay, like this. So here the okay, so we need to change the x and y values. So select data, edit the value of x. I want to plot as x values. The values on y axis I want to plot as h values. Okay, okay, that's fine. So here you'll see this side is head variation and this side is the distance. So in this plot, if you'll see, as in this case, we are assuming that the x is 0, where the x is 0, the head is 0, and the head is varying from 0 to 360 degrees. So in that case, the head is varying from 0 to 360 in this manner. Okay. So the head variation, the motto is to see that the head variation is not linear. It is having a non-linearity. Fine. Now, therefore, um, depending on this one, we can always use the Richards equation to plot the head variation in horizontally placed soil. Okay. And, now let's on move on to our question again. So we have determined what will be the variation in the head. So this type of variation is observed based on the value if we are taking k is equal to a plus bh, that is linear. So this is hydraulic conductivity. If we plot this hydraulic conductivity, then that's going to be a linear function because it is a equation of a straight line, a plus bh. But if we plot the suction head, then that's going to be non-linear. Then other equations were also provided for this head variation. The second one is from Lu and Lee-Cos. He have provided the head variation as this expression. Okay. where h is equal to 1 upon alpha. Alpha is a factor. Ln 1 minus qx alpha upon ks. So here the factor which needs to be determined from the experiments is alpha, and ks is the hydraulic conductivity at saturation. Okay. So based on the expression which we have saw, we are going to solve one more numerical. That's a steady state flow of water is taking place in a 100 centimeter long tube as given in the last question, placed horizontally. Okay, the head at one end is 0 meter and the other end is 360 meter. We need to determine the flow rate and also calculate the variation of suction head over the length of the pipe. So here the same things we have to determine Q and the variation in suction head H. And here the hydraulic conductivity is given as 8 centimeter per day at saturation. Alpha value is 0.02 centimeter per day. So which expression we'll use? We'll use the Lou-Henry-Cox expression given here. That's going to be Q is equal to, let's come back. We'll use this expression. H is equal to 1 upon alpha ln 1 minus Q x alpha upon Ks. So we'll use H is equal to 1 upon alpha, and that's going to be ln 1 minus Qx alpha upon Ks. Qx alpha upon Ks. Okay. So that is the expression which we are going to use. Let me just write it more neatly. So here it is ln, right? So in the first case, as we know that the value of h is given, and we know the value of alpha, and we know all the values. So we'll put value of head that is given is 360. So we'll write minus 360 here is equal to 1 upon alpha is 0.02, and here is going to be ln 1 minus the q we need to determine for the steady state, and the value of x is given 100 centimeter, and the value of alpha is again 0.02, and we determine it by the hydraulic conductivity at saturation. That's going to be 8. So if we try to solve this, then it's going to be 360 into 0.02. So minus 7.2 is equal to ln. Inside it's going to be 1 minus 100 into 0.02. So it's 2. So q by 4. Okay. And because ln is here, so it's a natural logarithm. So we write e to the power 7.2 will be equal to 1 minus q upon 4. And the exponential of minus 7.2, let me determine, minus 7.2 is going to be 7.46 into 10 to the power minus 4 will be equal to 1 minus q divided by 4. So if we take q here, then it will be q by 4 is equal to 1 minus 0.000746. So q will be equal to 4 times 1 minus something. This one is equal to 0.000746 is equal to 0.999. So q will be equal to 3.99, okay, centimeter cube per day, right? So here we determine the value of this steady state flow rate or the steady state flux, and based on similar to the last question, we can determine the value of this head variation with the distance, right? So let's do that. For this one, we again make use of the same formula. this, and here the Q will be known and X and H will be unknown. So let me erase the other part. Okay. So if we write here that head variation is unknown, that's going to be 1 upon 0.02, and ln, that's going to be 1 minus the value of Q is 3.99, let's say, and the X we don't know, and the alpha is again 0.02 upon the value of Ks is 8. Okay. If we simplify it further, then that's going to be 1 upon 0.02 is 50 ln 1 minus 3.99 into 0.02 divided by 8. So that's going to be 0.00997x. Okay. So based on the relationship which we have obtained, we can determine the variation in head over the length. Okay. So let's switch to Excel and do the same. Here we did it for the first expression, and then we are going to do it the similar for the Lewin-Lacoste expression. So let's go here. What is the expression we have obtained? Let's copy that one and come back to our Excel sheet here. Let's copy it here, and we are going to determine the head variation. This part. Okay, fine. So here we need to determine the head variation, and for every from x value of 0 to 100. Okay, and we have a component of alpha. The value of alpha is given as 0.02, right? And the head variation formulation which we have obtained here based on the steady state flow is this one. Okay, so we'll write h is equal to 50 multiply the natural logarithm ln. So we'll write ln and the bracket. What is the value inside? 1 minus 0.00997, and we need to multiply it with the x. So x value is q2 here. Okay, fine. And the head at 0 is 0. Moving further, we can determine the head variation from 0 to 100, right? And so if we plot this one, so if we the head at 100 should be coming at as a 390, as in last case 360, but somehow it's coming 290. So we'll need to cross check this question for the value we have obtained, maybe for the value of q, and then we can at the end, if we get 360 here, then our question will be verified. Okay, so let me just quickly draw this one also. Let's copy this graph, and we'll change the values which are used here. So x will be, let's change the data here. Select data, and we need to edit this one. The We are plotting this value, and the x value is given as, okay, there's no problem. X value is given as here x, and the y value will be the head variation. So the y value is going to be, give me a second, y value is going to be this one, and it's here. So it's, you see, in this variation also we can see the head variation with distance is highly nonlinear. Okay, here we can observe. So for the both cases, the head variation is coming to be nonlinear. Okay. So you can take some time on this question and see what went wrong while calculating the value of Q. If we rewrite this one, then that's going to be alpha into H is equal to ln 1 minus Qx alpha upon Ks. If we take the exponential, e to the power alpha into H is going to be equal to 1 minus Q alpha x upon Ks. Further simplifying, we can write Q into alpha into x upon Ks is equal to 1 minus e to the power alpha H, right? Further simplifying, we can write Q is equal to Ks upon alpha x 1 minus exponential to the power alpha H. Okay. Here, if we put the values, then what we'll observe, Q is equal to the value of K is 8. The value of Ks is given as 8. Okay, so these values which are here are for another question. So the K value of K is 8 and the values of alpha is 0.02. The value of x is 100 and the value of 1 minus exponential of 0.02 into 100. Let's solve this one. Let's see what we observe. 8 upon 0.02 multiply 100. That's going to be times 4 times and this one 1 minus e to the power exponential of 102 into 100. That's going to be minus 6.389 and if we multiply it by 4 it's going to give you around 25.55. Okay, so this q value we need to change while calculating and then only we can reach to the right answer. Okay, so before we move further, let's take a break of 5 to 10 minutes and then we'll move to the next question. Okay, so we were discussing about the flow through soils, and we have discussed about the head variation with the distance, and mainly in the horizontal flow. So now, for such conditions can also occur in the vertical flow, such as in the case of infiltration evaporation, as we have seen in this figure. Okay, so in those cases also, the using the Darcy's law equation, we can determine the variation of this head delta Hm and with the depth, right? So, like in this expression we have obtained, and the variation is given as dz is equal to minus dhm divided by 1 plus q by k. Fine. And if we consider a hydrostatic condition, in that case, what will happen? That the Q will be zero. There is no flow taking place. In that case, if we solve further, then we'll observe the variation of a matrix section over the depth is minus one. Fine. And if we take a case when the variation is with the depth is zero, then in that case we'll observe that the hydrostatic static the steady flow will be equal to the saturated hydraulic conductivity. Okay, so this expression can be wrote that Q can be smaller than equal to the K hydraulic conductivity function, and the Ks will always be greater than the saturated hydraulic conductivity greater than the flow rate. Fine. So moving on further to an example here, and in this example we are going to it's written that at a particular site, the steady state flow of water is taking place in a vertical direction. The flow rate of water due to evaporation is 10 to the power minus 8 meter per second. So the Q is provided as 10 to the power minus 8 meter per second. The drying data of volumetric water content, metric suction head, and the permeability for different sample are provided in this table. We need to calculate the height at which these particular heads will be occurring, right? So here in this table, if you'll see that observation number is provided, then the volumetric water content at this particular observation is provided, and the head is provided at this point, and the hydraulic conductivity is also provided at particular points based on the experimental data. And we need to determine the depth at which these hydraulic conductivities are occurring in a vertical direction. Fine. So for that, what we'll do is we will utilize this formulation that we have studied here that gives dz is equal to minus dhm, that is upon 1 plus q upon ks. Okay, use the eraser. Fine. This del dhm is the change in the this head at a particular depth. Okay, and if we will just determine want to determine the z, then we'll take a summation from I is equal to 1 to n. Right? So we'll do this stepwise. Okay, so the first step we can understand here that for the first one we can write the depth is zero. That's it. And taking the reference depth, and then if we'll go further for the second step, then we will calculate the dz or the small z will be equal to minus dhm, that is the change in head. What is the change in head? Let's say minus, and the change in head is s2 minus h1. So minus 0.001 minus minus 0.5, right, upon 1 plus the value of q is given as 10 to the power minus 8, and the value of k provided here is 5 into 10 to the power minus 7. Okay. So if we solve this, what we'll observe, zero point 0.5 minus 0.001, it's going to be minus 0.499 upon, here in the denominator it's going to be 1 plus 10 to the power minus 1 upon 5, 1.5. 0.02. Going further, 0.499 upon 1.02, that's going to be 0.489. And neglecting the negative sign. So it's going to be 0.489, right? And in similar way, we can solve for the second one, third one, fourth one. And to determine the capital Z, just write Z0 here. Then we will add this one with this one. Okay. So how we can do that? We will use Excel sheet for doing this calculation. So let's jump to the Excel sheet for the vertical flow. And here I've already noted down the data of these theta and hm and k. So, and we need to determine the values of z. Okay. So for that, if you'll see, let's delete this one. The value of q is provided at 10 to the power minus 8. So I'll write 1e minus 8. That's going to be 10 to the power minus 8. Okay. And the formulation we need to take from here, screen, this one. Okay, now we can do that here. So the values of theta is 0.41, 0.38, 0.35, 0.32, and etc. And the values of hm are provided here. Okay. And the values of z, how we can write is making use of this formula. Okay. So this minus is only for reference, so we can take positive in this case. And for z is equal to 0, we'll just write 0 here and 0 here for the reference. And moving further to the second observation, we will obtain what is the change in the head. That's going to be this value minus this value. So we'll write the formula is equal to the numerator will be this value minus this value. Fine. And the denominator will be 1 plus the value of q. That's going to be here and log this value divided by the value of k. The value of k is in D3. So we'll write D3 and we'll log this one also. Okay. And let's take care of the brackets. So it's going to be 0.4892 as we have observed here also 0.489. So if we use the similar formula for all the values, then we'll observe the values of Z, okay, or the depth at which these particular hydraulic metric suction values are being observed. And to write capital Z, we'll just need to take summation. So here we'll write the above value plus this value, right, which we are calculating. So every step this will update or this will be accumulated. So the value of Z is till 117 in meter, right? So here we can plot several things like the variation of metric suction with depth. We can also plot variation of hydraulic conductivity with depth and etc. Right. So this is one of the method how you can solve this vertical flow question for this condition of steady state flow. Okay. You can take some time to see if there are any doubts in this question. Okay. Continue. Okay, so this was the question we solved for the vertical flow, and similarly, we can solve another question. And for this one, this okay. So this question was solved for the drying data, the evaporation was taking place, and the second question we are going to solve for the wetting data. In that case, the infiltration is taking place. So the question is that at a particular site, the steady state flow of water is taking place in vertical direction. The flow rate of water due to evaporation is 10 to the power minus 8 meter per second. So the Q is provided as 10 to the power minus 8 meter per second. The wetting data of volumetric water content or the metric suction and permeability for different samples are provided here. And we need to calculate the height at which these particular heads will be occurring. Okay. So the formula basically will remain the same, just that the only value will change here is the sign of Q because this is the wetting data. So instead of water leaving the soil matrix, water is coming in. So we'll take this as negative value. Okay. So let's see how we can solve this one. So here, as we have seen that we write delta Z is equal to minus delta Hm upon 1 plus Q by K. And for this particular value, okay, it's not staying. So let me write it here. Delta Z is equal to delta Hm minus 1 plus Q by K. So for this particular value, if we write for the first one, it's going to be 0 and 0. For the second one, if we write, and then this will be minus 0.001 and the minus 0.5 divided by 1 plus Q value is going to be minus 10 to the power minus 8 and divided by the K value is 5 into 10 to the power minus 7. Fine. So if we'll solve further, then this will be minus 0.001 plus 0.5 minus 0.001 plus 0.5 making 3.499 0.499 divided by 1 plus and this is going to be minus 1 by 50. Okay. Solving it further, we'll observe delta Z is going to be 0.4499 divided by 1 minus 1 upon 50. That's going to be 0.509. So here it will come 0.509. So here also it will come 0.509. So these values now we can fill with the similar concept. So let's try down in an Excel sheet and see what values we are observing. Okay. So we will be using the same sheets and we'll solve this equation. Let's see how we can do that. Is we'll put the values of these values we can delete and now let's see for the first Z value we'll write is equal to what is the change in head that's going to be the first value minus the second value and divides by that's going to be 1 plus q upon k. The value of q is here, so I'll write it minus q and log this value upon the value of k is going to be this value. So the value of k is 3. 509 as we observed in this case here 0.509. So if we copy this formula from here to here, then we'll observe these values and the z cannot be negative, so we'll exclude these values. Okay, and here we'll write this plus this, and we'll go further and we can obtain the values of capital Z. Okay, and these values we need not to calculate, the Z is coming negative. Fine. So here again, we can plot the variation of z with k. We can plot the variation of z with height, etc. Okay. So take your time to look into this numerical once again, so that you can let me know if you have any doubts. Moving further with this question, then we solve the numerical for the drying data. We solve the numerical for the wetting data, and now we are on the concept of this wetting front. Okay. So when a head is maintained at one end of a soil sample, which is lying down horizontally, then the water will permeate from here, this end to that end, and a wetting front will be formed. Okay. This wetting front will move further as the time passes. Okay. So to determine the position of this wetting front, several researchers have given different concepts. And the Green and MT 1911 one, they use the concept of Darcy's law to derive the expression for the position of this wetting front, that is x. Okay, in respect to the saturated hydraulic conductivity, the H naught, the head maintained at this point, the HI head at this point, head at this point, and with the time. Okay, and have volumetric water content values. Right? So, to understand this concept, we will be solving one numerical on the position of the wetting front. Okay, and then we'll see that how the this position is calculated, right? Let me first erase this off and go to pen. So the example says for a horizontal soil sample whose one end is subjected to a water head of 0.1 meter. So let's say H naught is 0.1 meter, right? And the other end, the water and what volumetric water content at this end is given as 0.01. And initial volumetric water content is 0.01. So theta I is given as 0.01. Determine the location of the wetting front for different stamps and take values of Ks as this one, Hi as this one, and theta saturated as this one. So, so how we can do that? We will use this green and empty derivation that will give you the position of wetting front is equal to x is equal to twice Ks H naught minus Hi and divided by theta s minus theta I, and the time frame is always there. So if we put the values, let's say for the first one, so that's going to be square root 2 into the Ks value is going to be 5 into 10 to the power minus 5 into the H naught value is given as 0.1 and the Hi value is given as minus 1 meter. So it's going to be minus 1 divides by theta s. The theta s value is given as 0.45 meter minus the theta I value is given as 0.01 meter. Okay, and time at this point under root of t. Fine. Solving it further, we will write the inside value as 2 into 5 into 10 to the power minus 5 multiply 0.1 plus 1, 1.1 and divided by 0.45 minus 0.0. Okay, and the square root of this answer. So x will be equal to 0.0158 under root of 3. So this is actually with this expression we can determine the value of wetting front at a particular time, right? Okay, so so to solve this equation, what we are trying to do is that we are trying to determine the position of the wetting front at different time intervals. Okay, so we'll solve this numerically in Excel sheet and we'll see how we can do that here. So the horizontal wetting front question, we'll solve it here. So let's say um, we have a soil sample that is the length of the soil sample we can take like 6 meter. Okay, then at a particular time interval we want to determine that how this wetting front will travel. Okay, so when the wetting front will reach at a location of 0.05 meter, when it will reach a position of 1 and etc. Okay, so how we can do that is we'll come here and this expression if you'll see, if we rearrange this expression, what we'll obtain is that x square is equal to twice ks h naught minus hi, and it's going to be t divided by theta s minus theta I, right? If we solve it further, then it will give you the time stamp is equal to x square upon this expression of twice ks h naught minus hi and theta s minus theta I. Fine. So if we use this expression to determine the time stamps when the wetting front will be at a particular location, then let's see how we can do that. We reach here, and I type this expression here, removing these values which we are going to calculate. Okay, these values which are given in the question. Okay, fine. So the values of theta s. Let me type it. Theta S is given 0.45, theta I is given 0.01, H naught is zero point 0.1, Hi is -1, and the value of saturated hydraulic conductivity is zero point 0.5 liter per minus 5 meter per second. Right? So how we can write the values of time stamps when the wetting front will be at 0.01 meter, let's say. So to write this, we'll write T is equal to x square into theta s minus theta I. If we take this value above theta s minus theta I. So we'll write it here is equal to a bracket that's going to be x square. So a square, close it, multiply theta s minus theta I. So theta s is here, log this one minus theta I is here. Let's log this one too. Okay. Then we'll divide this expression by 2 times ks value. So multiply by h naught minus hi. So h naught minus hi, and we will close this bracket. Let's see what we are obtaining. So time stamp we have obtained here, and it will copy it from this one to this point. Then these are the time, and we need to take care of the unit also. So the value unit of x here is given in meter, okay, and the ks here is given in meter per second. H is also given in meter. These values are in meter and this is meter per second. Then we'll observe T as in second. Okay. So if I change the format of this one and change it to this decimal values, so in general number, increase decimal value to 4, write it okay. So these are the time stamps in seconds when the wetting front will be at this position, right? So in this way, we can determine the location of determine the timestamp when, or based on the timestamp t value, we can also determine the location. So we can do it in the other way also. If we have the timestamp value, then we can determine the value of x. by just reversing this expression. So it looks a little messy, so I'll request you to have a look in this question and let me know if there are any problem understanding this one. Similarly, the expressions have been provided for vertical flow also. So if there's a soil column placed vertically, then in the previous case we've observed that the only head that is contributing towards the flow of a front is the matrix section head. Okay, but in this case, if you'll observe that it's not only the matrix section head or the head which is maintained here, but also the elevation head which is responsible for this flow movement of the wetting front. So if we use the Darcy's equation again, then we will reach out to an expression like this by only cos. And in this expression, we can obtain that the value of t and z are unknown, and the other values will be known, so that we can determine the value of wetting front based on the time, or the time when the wetting front will be at a particular location. Okay. So let's make use of this expression and solve a similar numerical we solved in the last which slide for the horizontal flow. Okay. So the example is that for a vertical soil sample whose one end is subjected to water head of 0.1 meter. Okay. And so you can write that H naught is 0.1 meter. And the initial volumetric water content is 0.01. Theta I is 0.01. Determine the location of the wetting front for different time stamps. So take values of Ks this one, Hi this one, theta is this one. Okay, similar to the last case. Just that the expression will change. So now we'll just take this equation and we'll move on to our Excel for the vertical flow. And here we can observe that I've written the same in the similar format as for the horizontal flow. Okay, the value of theta s is provided as 0.55, 0.45, theta I is 0.01, h naught is zero point 0.1, hi is -1, and ks same to the last case. So everything is similar to the last case, just that the position of the wetting front in respect to the time lapse will change because of the this is a vertical flow, right? So here we have auto-determine the vertical position. So using this expression, we will write the time stamp values for a particular the position of the wetting front at a particular location. So let's see how we can do that. We'll write T is equal to, if we take Ks and theta s minus theta I this side, then T will be equal to, we will put a bracket. First we'll write theta s minus theta I. So that's going to be theta s minus value of theta I here. Okay. Then at the denominator there will be ks. Value of ks is here. Now close this one and we'll move on to the main expression, that is z minus this value. Okay. So we'll write a bracket, let's close this bracket, and we'll write z. The value of z is going to be a2. We need not to log this one minus the value of h naught minus hi. What is that? The value of h naught is 0.1. Log this one. Minus value of hi is this one. And log this one too. And then moving further here into the value of the ln, the natural logarithm. And inside we'll take always be careful of the brackets, and inside it's x naught minus hi plus z upon x naught minus hi. So we'll take one more bracket here, h naught. That's going to be this value log this one minus hi. That's going to be this value log this one and plus the value of z. That's going to be 82. Okay, close this bracket and divided by, let's take another bracket. That's going to be h naught again f4 minus hi 4 and close this one. So the timestamp you can obtain for each depth of the wetting front, okay, each distance of the wetting front in the vertical direction, that's here. So you see, for the horizontal one, you can also determine the position of the wetting front, and for the vertical one, you can also determine the position of the wetting front, right? Using these expressions. So here, the value for the first one, first z 0.01 is zero point 0.4, and we have observed the value of 0.39, so it's close. Second one is 10, we have observed 9.7. So it's the values are close, right? So take time on this numerical also. And let me know if you face any problem while solving it. So these are the two green and empty equations which we are discussing for the horizontal flow as well as for the vertical flow. Okay, so there are laboratory methods for defining the rate of capillary rise. That is actually the portion of the this wetting front based on the capillaries which are formed in the soil. And these are one of the setup and which you have already studied in the theoretical class. So some empirical formulas are there, the experimental formulas based on this, which we can determine the height in capillary rise C upon ED10. We've already seen those formulas of capillary rise P as a cos alpha upon Z. Okay, R. So these formulas we have already seen. Okay, theoretical formulas. Now we have empirical formulas also. Okay. So C varies from 10 to 50 mm square. Okay. D10 is the representative particle size and the E is word ratio. So the rate of capillary rise, uh, the expression by the Tabzagi is given as P is equal to this one. And in this expression, we have several values which we need to put. The value of this porosity, Fc, okay, and the value of PS, and then we have these values inside. So we'll solve a simple example for these values. Okay, so there are two soils. The value of porosity for each soil is given as the 0.31 and 0.21. The height is also provided here. The height of the capillary 0.284 and 0.82 meter, and the permeability is also provided here. Okay, so from here we need to define the time of this particular height of the capillary. Okay, so how we can do that? For soil one, let's say for soil 1, let's say we solve it. So we'll write T1 is equal to the value of N is 0.31, multiply the value of HC is 0.284, the value of KS is 1.6 into 10 to the power minus 4, right? And the value of ln HC, the value of HC is provided as 0.284 upon this again the value of HC 0.284 minus Z. Z is unknown because we are need to determine the time based on different values of depth. Okay, then we have minus the value of Z upon HC is 0.284. So if we provide different values of Z, okay, here, then we can determine the time and we can plot this graph. Okay, so how we can do that is by solving it in on Excel and plotting the graph. Let's see how we can do that. Coming here, first we'll copy the expression which is provided here. Okay, and the values I've already entered in the sheet. So okay, so how we can solve this is that I've taken different values of Z. Okay, and for both the sides differently. Okay, so it depends on what is the permeability of the soil. It varies. So we can also take different values for this soil. So let's say for soil one, if we are to calculate the time, the input values are provided here, and we'll use this formula to calculate the time at which the this wetting front will be at these depths, or the capillary ties will be at these heights. Okay. So let's see what the formula says. We'll write is equal to the first part is going to be porosity for soil one and log this one into HC and divided by value of KS. Okay, give me a second. So here we are trying to solve this example. Let's proceed. So here we have written the first term and HC upon KS. Now we move on to the second term that's going to be multiplied, and it is nothing but natural logarithm of HC upon HC minus Z, and HC is this one. Let's log this one for soil 1 and divided by HC minus Z, and again the HC value minus the Z value is going to be A2. And then we'll subtract the second term, that's going to be Z value A2 divided by HC value. So here we have observed the time, obtained the time, and if we formate this to the similar values of decimal value with the number decimal 4 and copy this for all the values here. Then here I've plotted the height versus time graph. So you'll see this time is in log scale. So you'll see this is the variation of this height of the wetting front due to capillary rise. Okay, for soil one. And we are going to do a similar thing for soil 2. So I'll just copy this formula here. Okay, and then I'll change the values. So this one is going to be here, this one will be here, and this one will again be here, and this one here, and this one here. So you'll observe that for soil 2, these values are like this. And after point 0.8, because the value of HC is 0.82 and this term is HC minus Z, you'll not obtain these values. So we'll delete these values and these values. So here for soil 2, the variation of height of the wetting front is like this. So after particular time, the height will rise significantly or very rapidly in soil 2 due to capillary head. Okay. So this is the numerical we have solved, and We can solve it by hand also, but to obtain the plots, this plot is not correct as you've seen in the theoretical class, and this will be the variation, right? And this is the variation for soil 2, this is for soil 1. So you can take your time to solve this example and let me know if there are any error or something. So this is based on the formulation provided by Tarzali and as we have seen here, and we've also used the Darcy's law to formulate it. And other expressions are also there, like Lou and Rico's 2004 expression. Richard's expression is provided for the diffusivity, using diffusivity value and the variation of head. And then we have Boltzmann transformation constant, etc. These we have studied in the theoretical class. Okay. So now we move on to the assignment questions. The first question states that steady state flow through soil can exist only in saturated condition. So as we have discussed in the starting of this class, that it is not so. This steady state is observed when a particular head is maintained at both the ends. Okay, and in like this case of vertical column, you'll see that not all the soil is saturated, but the soil in the middle is saturated due to this channel which have formed. Okay. So steady state condition is established, although the soil is not completely saturated. Okay. So this statement might not be true. The second question is that the outward flux from the soil in vadose zone during evaporation is dependent on the atmospheric temperature. So the outward flux actually depends on the change in head between these and these points. So as the elevation is already different, so it basically depends on the second thing is the suction head. And the suction value at the top here in the capillary, it depends on the temperature at the top. So if you remember the Titans formula, then from here you can also see that this value of saturated pore water pressure, it depends on the temperature based on the Titans formula. And it in turn determines then what is the suction value at the top. So this weather zone outward flux from the soil, it will also depend on the temperature of the atmosphere. So the outward flux from the soil in weather zone during evaporation is dependent on the atmospheric temperature. That is a true statement, right? So moving on to the third question, that is the hydraulic conductivity of soil can never be greater than the infiltration flux rate. So now we have studied in on the starting of the class as well as in the theoretical class that the hydraulic conductivity, that is Q of a soil, it follows this relationship. Okay, so the hydraulic conductivity is basically always lesser than the hydraulic conductivity at the saturation. Right? So this happens when the hydrostatic condition exists, right? So the hydraulic conductivity of the soil can be greater than the infiltration flux rate. So this infiltration flux rate is less, and the hydraulic conductivity at saturation or the hydrostatic condition is more, right? Then we have the fourth question that states the Green and MT utilize Darcy's law to formulate the solution of transient flow through soil. So the formulation of Green and MT, they have started from the development of the expression from the Darcy's law, okay, so that they can determine the transient flow equations of the soil. So it is quite true. They have utilized the Darcy's law to formulate this expression. The fifth question is that consider vertical column of partially saturated soil through which water flow is taking place, assuming that soil to be free of any salts. The flow taking place to the soil is due to the matrix suction head difference, only due to the matrix suction head difference in the soil. So, what is the head difference? It basically is the pressure head. Okay, in the soil it is considered at zero. Then we have matrix suction head. Then we also have osmotic suction head, and then we have the elevation head. Let's say elevation head. But here, as it says, assuming the soil to be free of any salts, so the osmotic suction will be zero. Pressure head we already considered as zero, and then we have this elevation head. So in the horizontal flow, this elevation has it zero. Okay, because the elevation of both the ends are same. But in the vertical flow, it's not so. In the vertical flow, this elevation has it important. Therefore, the statement that it is only due to matrix suction head, that is HM, is not true, right? So it is due to both matrix suction heads as well as elevation head. So here also in this expression, low and equals to 4, you will see from the book low and equals to 4, you can see that this depends on the elevation head as well as the matrix suction head, right? This is the question for the vertical flow. Then we have the horizontal flow, and the question asks that in a horizontal flow, yeah, if a horizontal flow is taking place for a partially saturated coarse grain soil column, in which constant head is maintained at boundaries, then the flux will be constant with time. Okay. So if we see the gain and application from where it has started, like the Darcy's law, then we'll see Q is equal to minus K dH upon dx. Okay. Here it is given that the soil is partially saturated in coarse grain and constant head is maintained at boundaries. So let's say here head is H1, here head is H2. Then dH upon dx is already defined. That is H2 minus H1 upon the distance, let's say L. So it is L, right? So this is constant and saturated for hydraulic conductivity is already a constant. So a constant and a constant. So Q will be constant. So the Q is not varying with time. It is constant with time, right? So this expression is correct that if a horizontal flow is taking place through partially saturated post-beam soil column in which a constant head is maintained at boundary, then the flux will be constant with time. Flux Q will be constant with time. So Q is not a function of time here. The seventh question is that the head variation with space across a horizontal unsaturated soil column for steady state flow is always non-linear. So the head variation with space across a horizontal unsaturated soil column for steady state flow is always non-linear. So if we take this condition of horizontal flow in unsaturated soil, and in the horizontal flow we only consider the matrix suction head, that is He, and if we use the Darcy's law to determine the variation is matrix suction head based on the values of x or the location, then we'll observe that H will be described by this equation. And in this expression, H is not linearly dependent on X. Right? So this expression is nonlinear. So it is true that the head variation with the space across horizontal and etc. for steady state flow is always nonlinear. So if you have any doubts to question 7, please do let me know. Now we coming to the eighth question, that is the solution to the Church equation. The yields unsaturated steady state flow behavior. In the Richard's equation solution, we'll see that at the end we obtain the expression for the transient flow, not the steady state flow. So transient is time dependent. So we obtain the expression for the time dependent flow. Therefore, the solution Richard's equation not steady state flow, right? Now we have study theoretical question. Now this question says that the soil is under steady state vertical infiltration of 10 to the power minus 8 meter per second. So the infiltration Q is provided as 10 to the power minus 8 meter per second, right? And the SWCC and hydraulic conductivity are established for such a condition. The metric suction head for two different volumetric water contents of theta 1 is given as 0.36, theta 2 is given as 0.39. And from SWCC, the volumetric suction at this point H1 is given as minus 2.5 and H2 is given as minus 0.5. So the hydraulic conductivity that is estimated K at 0.36 is estimated. 36 volumetric water content is expressed at 3.5 into 10 power minus 7 meter per second. And we need to determine the elevation headed meters at that point. Okay. So we'll be using this expression, which we have seen earlier, to determine the elevation head. That is equal to Z is equal to minus summation I is equal to 1 to N delta Hm, which is dependent on theta I upon 1 plus Q upon K, which is the particular theta I. Okay, so we have solved one numerical on this one also, taking different intervals in the head variation. So you people can try solving this question, and then I'll be solving this one. So as this, so how we can solve it? That we'll write the change in the HM values. That is going to be the H2 minus H1, and for the H2 is the minus 0.5 minus 2.5 divided by 1 plus infiltration. The Q value is minus, we will take it minus 10 to the power minus 8, and the K value is 3.5 into 10 to the power minus 7. So let's see how we can solve it. So it's going to be zero point 0.5 minus 2.5. Okay, so here we can write minus 2.5 minus zero point 0.5 divided by 1 minus, here it's going to be 1 10 to the power minus 1 upon 3.5, right? So here it will be minus 2 upon 1 minus 1 upon 35. That will be equal to 1 upon 35. And if we minus it from 1, so minus 2 upon 0.97. So minus 2 upon 0.97. That's going to give you minus 2.06 meter. Okay. So that's basically close to the value of 1.95. So we can take this solution of 1.95. Okay. While solving, please cross check if there are any errors. Then we have this last question, which says the head variation with depth in a vertical column of saturated soil is non-linear when the head at the top boundary is varying with time. So from the basic formulation, if you'll see, if a particular head is maintained, that is H, okay, then the head variation at a particular, that is delta H upon delta X, that is called this hydraulic gradient, right? And in the saturated soil, this hydraulic gradient is always constant. So if you go at a particular depth and measure the head here, then this ratio delta Hi upon delta Xi will always be constant. Even if we change the head, okay, and uh, even if we change the head, okay, this will be a constant value. So the head variation with depth in a vertical column of saturated soil is linear, not non-linear. Okay, even if the head is changed at the top boundaries. So these were the questions which we needed to cover, and now I leave it up to you people. If you have any doubt, please do let me know. I'll be waiting here for a while, and kindly let me know. Okay, so if you have any question later on, kindly do let me know, or in the next class also we can cover those. So thank you everyone for joining, and I'll be closing this meeting now. Thank you for joining. We'll see you in the next class.